Are you plugged in?
Yep.
It's got the reverb on. Go ahead. Okay, that's pretty loud. Welcome to episode 8. Today we're going to dive into Fourier and fast Fourier transform concepts in circuits. And we'll use music in some of our examples. But you may know that this area of ECE has broad application. For example, it's used extensively in wireless communications. And there are a lot of excellent YouTube videos already out here. But when I sample them, it appears that most, if not all of them, dive pretty deep into the mathematics involved. And that's fair, of course, because Fourier is, in fact, a mathematical subject. So, what are we hoping to do in this video? These are the guiding principles for this video. I wanted to provide an intuitive understanding with minimal mathematics prerequisites required. So if you've seen some of our other videos and you've gotten through them, you should have no trouble in this video. Even if you haven't seen them, they're not a prereq for this video. However, a little bit of algebra is, and you'll see some of that as we go. We're also going to sprinkle real-world examples of Fourier series throughout. In fact, let's do one of those right now. This is from a demo that we did in one of the electronics courses that we are teaching. And one of the students volunteered to bring in his guitar, and he can play and I can't. So I'm going to play you a little clip from this. All right, so the good thing is there's no buzzing. Go ahead and just play a little bit. Very nice. So the left side of the screen was displaying the waveforms, and the right side was displaying the spectrums. And I'm going to try to insert examples like this throughout today's video. We're also going to do some examples of using this material in circuit analysis, and ultimately then you could use it in design. How do we understand, for example, what this guitar amplifier circuit is doing? So let's get into it. Here's the high-level view of what we're going to talk about. Let's dive into the time and frequency domain material. This video actually gave me a good excuse to buy a guitar and try to learn it. And I'm going to play a single note. It's the note E, first string on the guitar. And I'm just going to play that one note so that we can kind of focus on what's going on in these displays. So the tonal quality depends on a number of things. How hard we pluck the string, where we pluck it to some extent, but also the pickups being used, etc. One thing you might have noticed is that it varies with time after you pluck it. But for any sufficiently short period of time, like the 20 milliseconds shown here, it's a repeating waveform. We call this a periodic waveform, as many of you know. This scope is set on 2 milliseconds per division for the waveform, and so this is 1.5 divisions between the peaks, and so that's 3 milliseconds. And we call that T0, the period of the waveform. On the right-hand side, I'm using the fast Fourier transform in this oscilloscope to look at what we call the frequency content. And we're going to get into that a lot today, so don't worry if that doesn't immediately evoke all kinds of knowledge. What I will point out here, though, is that this is a plot of frequency on the horizontal axis and amplitude in dB relative to a volt on the vertical scale. All you really need to know is horizontal is frequency, vertical is a dB scaled thing, and it's about 10 dB per division. So there's clearly something here at 330 hertz. That's what we call the fundamental. And then this is going to be called the second harmonic, third harmonic, and so forth. Later on, as the string decayed down a little bit in volume, the scope captured another 20 millisecond frame, and the spectrum looks like this. So we have waveforms on the left, spectrums on the right. For whatever reason, we call this the time domain, and we call this the frequency domain. That makes sense. And that brings us to Fourier. Fourier is the bridge between those two domains. How do you go from a time domain waveform to a frequency domain spectrum, or the opposite direction? Well, the answer to that is covered in university courses. At the school I was teaching at, Fourier theory was covered mainly in the junior year. But it is actually possible, if we had the time, to insert it into something like this Introduction to Electrical Engineering course. We're going to talk through how all this stuff works without relying on calculus, for example. But if you are familiar with that material, we have at least one slide where we'll go through it for the case of a square wave. But before we get to that, here is the basic concept of Fourier series. It's pretty straightforward. Fourier theory states that any periodic waveform, you remember those waveforms we were looking at a second ago are periodic, they repeat, can be decomposed in a sum of sine waves with what are called harmonically related frequencies. And here's an example of doing that with our guitar waveform. We have a signal, S of t. That's the guitar waveform. You can see it here, voltage versus time. Fourier theory says that we can decompose that into a sum of sine waves. So we take a bunch of sine waves and add them together. What does that mean? Well, in this graphical representation, it means that, for example, at t equals 0, we have this value, where this line is crossing the vertical axis, and we add it to this value where this fundamental sine wave is crossing the vertical axis, added to this value, and added to this value. And if you add all those values up, you get the value of the waveform at t equals 0. So the mathematics will allow you to come up with very precise amplitudes and phases of these so-called harmonics, these different frequency waveforms that you add together. Here I've just tried to provide a notional view, and I think I got it reasonably good. Let's take this time right here, when this one is a negative peak. Notice that this one is also a negative peak. This is 2 times the frequency of the fundamental, and they're both lined up, and so that's going to add to that, and is also going to add to this one, and so we get a very deep negative peak there in the full waveform. And if you do that for every time t, adding the values of each of these waveforms together at that specific time and plotting it over here, you should get a waveform that looks like the original, if I got the amplitudes and phases correct over here. If we use the language of mathematics instead of a graphical form of talking about this, we can write what's shown on the right-hand side. This is the so-called trigonometric Fourier series because it uses cosines in this case. Sometimes you'll see it written with sines and cosines, but here we're using cosines and frequency and phase information. Now, I was tempted to stop here with this exposition, but I think it's important to understand that if you study this material in detail, then you may see material like this. It's not critical for today's episode because we're going to use the oscilloscope and FFT to evaluate what the spectrums look like. However, if you do university work, then you do integrals. And here they are. I'm just going to zoom in on them and pause briefly on each one, and you can study it at your leisure. What this is the general form on the left, and then we compute the coefficients for a square wave, which we'll look at using the scope soon, and then you can plot the spectrum as shown over here on the right. So let me just zoom in real quick, and you can pause it or fast forward depending on whether or not you want to look at it. Here's the expression for, here it's called f of t instead of s of t, but here's the expression in terms of cosines and sines, and here are the expressions for evaluating what the a sub n and b sub n coefficients are. Then you can map it into the expression that we had as shown here. For a square wave, which now I'm calling s of t, looks like this graphically. And we know that we can expand it into a sum of sines and cosines or cosines with phase angles. And so here's an expression for that. And then we do integrals to find the a sub n and b sub n values. You can check it, see if I made any errors. And here's the result. Turns out that for this particular square wave, which looks like that, you can express it using only sine waves. Or you can express it in terms of the cosine with phase angles that I talked about earlier. And finally, here is the plot. And for a square wave that goes between +1 and -1, the magnitude of the fundamental is actually bigger than +1. It's 4 over pi. There is no second harmonic. There's a third harmonic, and it turns out to be, according to this expression, 1/3 the height of the fundamental. There's a fifth harmonic, 1/5 the height of the fundamental, and so forth. And all of the phase angles here are -90 degrees. Now, in practice, you don't do integrals very often. In practice, we typically use test equipment to figure this stuff out, or computer programs. Here, I set up a cheap signal generator that I have. It's at 0.00033 megahertz, which is 330 hertz. And it's a square wave with a 50% duty cycle, which seems kind of redundant because, right, a square wave should be square. Anyway, and here it is in our time domain and frequency domain displays. And what I've done is I've selected the math function on the oscilloscope here and then gone into the menus and configured the fast Fourier transform, or FFT, to show as we have it on the display. I had to scale it from 0 to 5 kilohertz. That was the range I was interested in because of the audio we're dealing with. And the amplitude I set to have a reference level of 0 dBV and 10 dB per division vertical scale. Now, note that this vertical scale is in dB, dB relative to a volt. So 0 dBV at the top here would be an amplitude of 1 volt. Minus 20 dB here would be an amplitude of what? From those previous videos, that would be 0.1 volt. So it is a little tricky sometimes when dealing with an FFT to map from dB domain to what's called linear domain that those mathematical expressions had in them. But it just takes sitting in a quiet room and working through this a couple times on a piece of paper to try to understand it all. Here, I'll just walk you through the fundamental. It looks like it's 0.6 divisions down. So this would be like -6 dBV at this peak. If you watched our previous video, you may know that -6 dB is 0.5 in voltage. And that does match the peak over here on the left, 0.5 volts. This was a 1 volt peak-to-peak square wave. But if you're watching closely, or if you've seen the series for a square wave before, you know that the fundamental amplitude should be 4 over pi. And this is a little bit different than that. I think that's because this is probably an RMS voltage. In any case, the fundamental is about 0.5 volts in amplitude. The next harmonic in the square wave, which is non-zero, is in fact the third harmonic. So this was 330 hertz. This is about 990 hertz, about a kilohertz. Its amplitude is 10 dB lower than this one, and that's because it's 1/3 in voltage of the fundamental. Now, as the note says at the bottom, we often just look at the amplitude spectrum. In fact, I don't even know if this oscilloscope can display phases for me. So the question is why? Well, we're going to get into that a little bit later, but basically it's because it's audio and your ear doesn't in general respond to phase information. There are special situations where, yes, phase matters, but in general it does not for listening with your ear. Okay, now here's an interesting, fun experiment. Remember what we're saying. We're saying that a square wave can be built from a bunch of sine waves. I don't know about you, but when I first look at square waves, I'm thinking to myself, how in the heck is that the case? I mean, I don't see any sine waves here. I see sharp edges, and that's about it. But supposedly, there are sine waves in this, which means that if I ran the square wave through something like a bandpass filter, which you see on the left over here, I configured it at 1 kilohertz, that I could select out the individual sine waves that make up that square wave and see if it's real. Well, guess what? It is real. This is a so-called multiple feedback op-amp filter. You can find ways to design this searching on the web. And I designed it, I think it was a Q of 10 or something. And so it's a very sharp peak at 1 kilohertz. The idea is to reject 330 hertz, which is down here, and likewise with the higher harmonics. And lo and behold, when I built it up and looked at the output, I got the third harmonic out. Remember, the filter is 1 kilohertz. This square wave was at 330 hertz. So I'm pulling out the third harmonic, which is 990, which is 1 kilohertz. Anyway, pretty cool, I think, that you can actually pull out the third harmonic from something which is not made. The signal generator does not make this by adding a bunch of harmonics. It's simply switching voltage from here to here. So all this theory is very, very real. Okay, so that's how to find and interpret the spectrum of a square wave with and without messing with integrations. Now, there are many other waveforms that are important, and some of those are handled mathematically in textbooks and classes, but some are like the guitar, which there is no real mathematical expression for except for the Fourier itself. But in a textbook, after you do a square wave, you might do something like a pulse train. So here I've done it with the oscilloscope and the signal generator, which I've configured to be a so-called square wave, but with an 8% duty cycle. So it's not square, it's a pulse train. And we can see the result here. We have these sharp pulses and then a long period of time for the next one. So it's high for 8% of the period of the waveform. The period I left at 3 milliseconds, which is a frequency of 330 hertz, which is here, the fundamental. Notice what's different now, though. A couple things. Number one, there is a DC component. So here at 0 frequency, we have a very strong DC component. That's because the waveforms spend a lot longer time at negative 500 millivolts than it does at positive 500. So the average DC value is close to negative 500 millivolts. Of course, this scale on the right is dB of the magnitude, and so the negative 500 becomes 500 millivolts, and it's about negative 6 dBV. The other thing that's drastically different is the number of harmonics. It stays almost flat out through many harmonics, and there are even harmonics, not just the odd harmonics like there were with the square wave. It does, however, at very high frequencies roll off in amplitude. Looks like it comes back up a little bit, but in general, waveforms will roll off at some upper frequency, which we call the bandwidth of the waveform. This one, I'm just going to use this dip here as a measure of that. Looks to be about 4.2 kilohertz. When you work this out analytically using mathematics, what you can come up with is a formula for where that null will be. How many harmonics you'll have, or what frequency range over which you will get decent amplitudes before you reach the null. And it turns out that it's 1 over the time of the pulse width. So here we have a 3 millisecond period, but the pulse width is 8% of that 3 milliseconds, or 0.24 milliseconds. If you take 1 over the pulse width, you get where that first null is in the spectrum. That is an important thing to remember, because this waveform, even though it may look academic, is quite applicable in many situations. Remember I said at the beginning that Fourier is used not just in audio, but in many, many areas of electrical and computer engineering. Here we have a cell phone tower, and we all know about cell phones and how you can send high rate data like videos and so forth. But what's the penalty for sending those high rate videos? Well, they have high bit rates. And although this waveform is not itself a bit stream, unless of course you want to interpret it as a 1 followed by a whole bunch of zeros followed by a 1 and so forth, but if you had random data whose bit period is the same as this pulse width, and you know what that pulse width is because it's the bit period, so maybe you have 1 megabit per second data, that means you'd have 1 microsecond, so you'd have 1 over 1 microsecond, which would be what? 1 megahertz. So a 1 megabit per second data waveform turns out occupies a bandwidth of about 1 megahertz. If you want to send 100 megabits per second, then you've got to have 100 megahertz of bandwidth. And the cell phone company doesn't like that because there's not that much, well, there's that much bandwidth, but you need to share it with hundreds, thousands of other people all sharing the cell site. But never fear, the people who have gone into this material in depth with the mathematics have come up with some ingenious ways of cramming 100 megabits per second into a much more narrow bandwidth. We're not going to cover that here. So that brings us to the third and final topic in this episode, but I think I'm going to leave that for a part 2. In that part 2, we're going to come back and look at guitar waveforms and spectrums and look at this part of this circuitry. We've seen the other parts in previous videos and we will review it in part 2, but we're going to focus in on this area, which in the block diagram that we did in a previous episode, we labeled audio response shaping. It'll take our guitar waveform and turn it into a different waveform, but more importantly, a waveform with a different spectrum. So we're going to figure out what that spectrum will be and what it means in terms of what it should sound like. That's why they're doing it, to make the guitar sound special. But we've covered enough in this video that you, I don't know, hopefully you might want to go out and download a cell phone app that does an FFT. I have an Android phone and I found one called Spectroid, which I really like. It doesn't show it here, but I think it has like 4.7 stars. So it's highly rated. And this yellow line is the FFT. And it'll do a log scale here, or you can change it to a linear scale. And you can talk into it or sing into it and see what frequencies you produce. This was me trying to hit the 330 hertz E that we had on the guitar. Looks like I hit 319 hertz. Not horrible, I guess. I don't know. I did try to find this on the Apple Store and I couldn't find it. So I found this one, but I know nothing about it. Looks like maybe down here it's got an FFT similar to the Spectroid. Okay, that's it. I'm going to cut it off here for this part 1 of episode 8. And I hope to see you in a future video, which will be part 2. And I'll leave with replaying some of the guitar and looking at the spectrums. All right, so the good thing is there's no buzzing. Go ahead and just play a little bit.